Welcome to this video on sampling distribution of slopes. By the end of this video, you should be able to identify statistics and parameters for linear regression, and you should be able to use the sampling distribution of slopes to evaluate a claim. So our first scenario that we're going to talk about is, do students who sit in the front rows do better than students who sit in the further away? The question is this an observational study or an experiment? What it doesn't say is I made a seating chart. I assigned the students to these rows, so we're going to call this an experiment because a treatment of row assignment was imposed. Okay, we are given the 5 different rows and then the scores of the students who are sitting in those rows. So why is it important for us to randomly assign the students to seats rather than just letting people pick wherever they want to sit? Because I'm wondering, does seat location matter? We want to have a random assignment so we can show causation. All right, so we can show causation. The variables that we have row and score, so there are 2 variables, and they are quantitative because they're all reported in numbers. Okay, our explanatory, what explains our outcome, because the question is about, does row matter? So row is the explanatory, and their grade in the class or their score is the outcome. All right, so I went to Staplet and I put all of this data in for you. So let me show you what it looks like. So you can pause the video and copy this down. So this is our scatter plot of the data. So go ahead and pause, take a second, pause, and write this into your paper. All right, so in our graph, you would have noticed there is a line going across it. This is actually your least square regression line. Okay, and so it comes across to about there. Okay, so that's your least square regression line. Now let's take a look to get the equation from that line. So looking at our information, we're going to come down here, and it gives us the printout. We could have put all of this into our calculator with the row in list 1 and the score in list 2 and gotten all of the same information. Okay, so I have, now remember, we like to use context. So our Y values are our scores. So make sure that we've got that written onto our paper, that our Y values are our score, and our X value is the row. So when we're predicting the Y hat, we're actually predicting the score. So we're going to do that. I'm predicting the score, and that equals 85.95 minus 1.517. And the X value, I don't want to put X, I want to put the word row. That way, if there's ever a question, you know where to plug everything in. Okay, so the slope of our least square regression line is negative, and we can see it starts off higher and it goes down as it goes left to right. So negative 1.517. And so to interpret it, let's review that quickly. When you're interpreting slope, you're saying for each additional X value, and our X value in this case is a row. So for each additional row, a student's predicted their predicted score will decrease by 1.517 points. Decreases by. So we included a lot of context around here. So whenever you're interpreting slope, you'll say for every additional X value, whatever it is. So in this case, it was rows. For each additional row, a student's predicted, because that's what we're asking, is for a predicted score. Their predicted score decreases by 1.517 points. All right, so let's flip this over and see what we're going to do with this. So does this negative slope provide convincing evidence that sitting closer causes higher achievement, or is it plausible that the association is purely by chance because of random assignment? So in order to investigate this question, purely by chance, I collected some data. We're wondering if we assume that seat location has no effect on the exam score. Okay, if we're assuming seat location has no effect on exam score, that is actually a hypothesis. That's a null hypothesis, the no effect. And so slope, we'll talk more about this notation later. Big B for the population slope, we're saying the population slope is 0, where B is the true slope of the population least square regression line. And we'll call that least square regression line like we did previously. Okay, so we made a hypothesis and then we defined what our parameter is. Okay, so give me a second. I'm going to give you all of this data and then I want you to go calculate the regression line slopes by putting the rows in list 1 and the scores in list 2. All right, here is all the data that was collected. In just a second, I'm going to ask you to pause the video to write this all down and calculate the least square regression line, but I want to remind you how to make this happen. All right, so the easiest way that I found to do this was because row number is your X, I went through and put in 6 of each row number. So 1, 1, 1, 1, all 6 of them. Okay, and then I went back and put in all of my scores. So then 2, 2, 2. Okay, that was the easiest way. So go ahead and put these in and calculate your regression line. And to do that, remember you're going to press Stat and then go over to Calc. And you're going to choose, usually it's number 8. You want it to say Lin Reg A plus B X, and your B will be your slope. So go do those and come back and see how you did. Okay, after calculating all of these out, I got a positive 0.9167 for the first set, 1.983 for the second set, and negative 0.2 for the third set. So what we're looking for here is if seat has no effect on exam score, just by random, purely by chance, can we get a slope as extreme as what we found? Okay, so let me show you what we got as a whole. All right, so we had 90. All right, so I don't want you to put all 90 of these on here. I want you to do a quick sketch so you get an idea of what the distribution looks like, and then come back and we'll continue. All right, so remember you want just kind of a rough sketch. Now, remember our slope that we got was negative 1.517. So I'm going to put this in here, negative 1.517. That was the overall from that particular issue. So here, all of these guys. So there are 12 dots in this selected area. 12 out of the 90 samples were as extreme as ours. Okay, so let's take a look at this. 12 out of the 90. So when we take 12 divided by 90, we get 0.133, and it's going to keep repeating. 13% of the time that happened to get a slope this extreme or more purely by chance, 13% of the time. Not that uncommon. So, to me, that's going to be a fail to reject the null. It happens with enough regularity. It's not terribly unusual. So let me remind you what this is. This is we did a randomized experiment, so this is a randomization for slope. And because we were using samples, we're going to use the little b there. All right, so let's flip this over and summarize some of this information down for you. So there's a couple things I want to remind you that when you have a population, so I'm going to make a little population cloud here. So for the population, we're going to say the mean of y equals, I'm going to use alpha, but it's not a significance level, okay? It's just the letter A. A plus bx. This is what the population line looks like, okay? We take a sample out of it, and when we take a sample, the equation that we use is very similar, but the notation is different. We use y hat equals A plus bx. So it's just different notations. And then, of course, we like to put, for y hat and for our x, we like to put context words there instead of those letters would be better. Okay, so let's look at our parameter versus our statistic notation. So when you see it written down, you know what you're looking at. So we have our y-intercept we're going to talk about. We have slope. We have the standard deviation of the residuals. And then we have the standard deviation of the slope. Okay, so we're going to give the statistic notation and the parameter notation. So we have our statistic and we have our parameter. That way you know what you're reading when you're looking at all of this symbology that's going on. So the y-intercept, we always said it's stat calc 8 because it's A plus bx. A is your y-intercept. This is the sample. Sample tends to be in English letters. Parameters tend to be in Greek letters. So the Greek letter for A is the alpha, but it's not an alpha level. Remember, this is just because that's representing A. It's A plus bx, so our slope is b. The population is this scrolly b. Okay, your standard deviation of the residuals for the statistic, it's just S. It's sigma for your parameter. We should remember that. And then the standard deviation of the slope. When we're talking with a statistic, it's no longer, we don't call it standard deviation any longer. It's the standard error. And we're going to put a little b there for slope. Or standard deviation of the slope. It has a little b to help us remember. Okay. And then the last part is you're going to have to draw some curves for shading on some of these things when we're finding area. Okay, so we're going to be centered on 0. This is going to be a normal curve with a mean of 0, and the standard deviation of the slope is going to go here, and it's more than likely actually going to be the standard error of the slope. All right, so what I want you to do, well, let's do a quick little review. You're going to do this check your understanding, and for whatever reason you cannot really see the chart that's here. So let me show you this chart. Okay, so this is a regression analysis. It's a mini tab. We've seen this multiple times. This is age versus ear height when you go back and read the whole scenario. So I wanted to remind you of some of the things. So where it says constant, that's your y-intercept. Okay, so the constant is 2.8871. Below that, whatever it says, this is your slope. Okay, hopefully that will help. And then we have our standard error that you can see right here, standard error. Okay, and you have two different numbers. You have standard error of the y-intercept and you have standard error of the slope. So just be able to read both of those. Then this little piece right here, that S, that's your standard deviation of your residuals right there. Okay, so you want to take this and you want to answer the questions down below. So keep it like this if your chart doesn't show up on yours, so you can see all the numbers and what we talked about. Notice over here, so we've got our R squared. That's how well does this line predict. That's 82.5%. That's pretty good. Then you have T and P. These are P values and T scores, depending on what we've got, whether we can there's different reasons being able to use that, but we're not really going to be talking about that. The big things is your y-intercept, your slope, your standard deviation of the residual, and the standard error of the slope. All right, so go ahead and answer these questions. Check the key online. Hopefully that was helpful. Let me know if you have any questions.